Россия входит в пятерку мировых лидеров по разработке и выпуску авиационных и ракетных двигателей.
Have you ever heard of Russia's GTD 110M engine? If not, you're looking at one of the most significant developments in Russian industrial engineering in decades. This isn't just another turbine sitting in a power plant somewhere. It's a machine that represents a complete shift in how Russia approaches energy independence, and the technology behind it has implications that stretch far beyond electricity generation. The story of how this engine came to be involves crisis, determination, and a race against time that forced an entire nation to rebuild capabilities it had lost. So what pushed Russia to develop something like this in the first place? Let's rewind a bit to understand the pressure that made this engine necessary. The crisis that sparked innovation. For decades, Russia's energy infrastructure leaned heavily on Western technology. After the Soviet Union collapsed in 1991, the country lost a significant portion of its skilled engineering workforce, manufacturing facilities, and the technical know-how required to produce advanced industrial equipment domestically. Turbines, which are essential for power generation, became one of those critical imports. Companies like Siemens and General Electric filled the gap, supplying Russia with high-performance gas turbines that kept the lights on across the country. At first glance, this arrangement seemed practical. Western turbines were reliable, efficient, and represented decades of refined engineering. But this convenience came with strings attached. Purchasing these turbines was expensive, and the costs didn't stop at the initial sale. Maintenance, repairs, and technical support all required foreign expertise, creating an ongoing financial drain. Russia found itself in a cycle where it paid billions to foreign companies just to keep its energy grid functional. Then came 2022. Geopolitical tensions escalated and Western sanctions hit hard. Siemens and GE, along with other major suppliers, pulled out of Russia entirely. Suddenly, there were no new turbines coming in and no support for the existing ones. For a country as vast as Russia, with extreme climates and massive energy demands, this was more than an inconvenience. It was a genuine crisis. Power plants that depended on these turbines faced uncertainty about how long they could keep operating without replacement parts or technical assistance. This moment became a turning point. The Russian government and its industrial sector realized that relying on foreign technology for something as fundamental as energy was a strategic vulnerability. The urgency was clear. Either develop domestic alternatives or risk long-term instability in the energy sector. That pressure gave birth to the GTD 110M project, an ambitious effort to create a completely Russian-made gas turbine that could match or exceed Western standards. Building a turbine from the ground up. Creating a gas turbine capable of competing with established Western models is an enormous technical challenge. Rostec Corporation, a massive state-owned conglomerate overseeing defense and industrial technology, took the lead. They partnered with Power Machines, one of Russia's largest energy equipment manufacturers, pooling resources, engineers, and research capabilities from across the country. The team faced a steep learning curve. Modern gas turbines operate under extreme conditions, with internal temperatures reaching well over 1,000 degrees Celsius. The materials used must withstand not only intense heat, but also high pressures and continuous mechanical stress. Precision is everything. Even minor flaws in design or manufacturing can lead to catastrophic failures. And failure did happen. In 2017, during the early testing phase, one of the prototype turbines exploded. It was a harsh reminder of just how unforgiving this technology can be. The incident could have ended the project, but instead it became a learning moment. Engineers analyzed what went wrong, adjusted their designs, and improved their manufacturing processes. This trial and error approach was necessary but time-consuming. Material science became one of the biggest hurdles. Western manufacturers had decades of experience developing specialized alloys and coatings that could handle extreme turbine conditions. Russia had to either redevelop those materials from scratch or find alternative solutions. Domestic research institutes and universities were brought into the effort, focusing on metallurgy, thermodynamics, and precision engineering. Testing was relentless. Every component had to be validated under real-world conditions. The turbine blades, combustion chambers, and cooling systems all required iterative improvements. Each test provided data, and each dataset informed the next round of design adjustments. Slowly but surely, the GTD 110M began to take shape, moving from concept to functional prototype to a machine capable of reliable operation. What makes the GTD 110M special? So what exactly is this engine capable of? The GTD 110M is a gas turbine designed primarily for power generation with an output capacity of 110 megawatts. To put that in perspective, that's enough electricity to power a medium-sized city or support large industrial operations. It's a significant amount of energy packed into a relatively compact design. Efficiency is one of the turbine's standout features. Modern gas turbines are judged not just by how much power they produce, but by how much fuel they consume in the process. The GTD 110M achieves a high thermal efficiency, meaning it converts a greater percentage of fuel into usable energy while minimizing waste. This translates to lower operational costs and reduced environmental impact, both of which are critical in today's energy landscape. The design itself reflects years of refinement. Compared to older turbine models, the GTD 110M is lighter and more compact. This makes it easier to transport, install, and integrate into existing power infrastructure. Despite the smaller footprint, it doesn't compromise on performance. The engineering team managed to balance size with power output, a feat that requires careful optimization of every internal component. Durability is another key aspect. The turbine is built to operate continuously under demanding conditions, with components designed to withstand extreme temperatures and pressures over long periods. This reduces the need for frequent maintenance and increases the overall lifespan of the machine. For power plants operating in remote or harsh environments, this reliability is invaluable. How does it compare to Western equivalents? Turbines from Siemens and GE have been the industry standard for years, known for their efficiency, reliability, and advanced control systems. The GTD 110M is competitive in these areas, though it's still a newer design without the same decades of field data that Western models have accumulated. However, the fact that Russia developed this turbine independently, under sanctions, and within a relatively short time frame, is a testament to the engineering capabilities mobilized for the project. From power plants to potential aviation uses. At first glance, a power generation turbine might seem worlds apart from an aircraft engine, but the underlying principles are remarkably similar. Both rely on gas turbine technology, where air is compressed, mixed with fuel, ignited, and expelled to produce thrust or drive a generator. The core mechanics overlap significantly, which is why advancements in one area often influence the other. Efficiency, weight, and reliability are critical in both power generation and aviation. For aircraft, every kilogram matters, and engines must perform flawlessly under extreme conditions, from freezing high-altitude environments to the intense heat of takeoff. The materials and engineering techniques developed for the GTD 110M, particularly in handling high temperatures and pressures, are directly applicable to aviation turbine design. Russia has a long history with jet engine development. During the Soviet era, engines like the Klimov RD-33 and Saturn AL-31 powered military aircraft and became known for their ruggedness and performance. However, after the Soviet collapse, the aviation engine sector faced many of the same challenges as other industries: brain drain, outdated facilities, and a loss of technical continuity. The GTD 110M represents a resurgence of those capabilities. While the turbine itself is designed for stationary power generation, the research and development behind it have revitalized Russia's broader turbine engineering sector. The lessons learned in material science, precision manufacturing, and efficiency optimization can inform future aviation engine projects. Adapting a power turbine for aviation use isn't a simple plug-and-play process. Aircraft engines require specific thrust-to-weight ratios, rapid throttle response, and the ability to operate reliably across a wide range of altitudes and speeds. But the foundational technology is the same, and the expertise gained from the GTD 110M project puts Russia in a stronger position to develop or improve aviation engines domestically. Real-world impact across Russia. So where is the GTD 110M actually being used? One of the most notable installations is at the Utrannaya power plant in the Krasnodar region in southern Russia. Before the turbine was installed, the plant had a generating capacity of 454 megawatts. With the addition of the GTD 110M, that capacity jumped to 560 megawatts. That's a substantial increase, providing enough additional electricity to cover roughly 10% of the region's total demand. The Krasnodar region is an important economic zone with a mix of agriculture, industry, and growing urban centers. Reliable electricity is essential for everything from food processing plants to residential heating systems. The GTD 110M helps ensure that the local grid can handle demand spikes, particularly during extreme weather when energy consumption surges. Beyond Krasnodar, the turbine's deployment has broader implications for Russia's energy security. By reducing dependence on imported technology, Russia gains more control over its energy infrastructure. If foreign suppliers decide to cut ties again, the impact is far less severe. Domestic production means that replacement parts, technical support, and future upgrades can all be handled internally. The economic benefits extend beyond just electricity generation. Manufacturing the GTD 110M creates jobs across multiple sectors: engineers designing components, factory workers assembling turbines, technicians installing and maintaining them. This ripple effect strengthens local economies and builds a skilled workforce capable of tackling future technological challenges. Other regions are beginning to adopt the turbine as well. Russia's energy needs are vast, and many power plants across the country still rely on aging equipment. The GTD 110M offers a viable domestic alternative, and as production scales up, more facilities are expected to integrate these turbines into their operations. Each installation represents another step toward full energy independence. The road ahead and remaining challenges. Developing the GTD 110M was a major achievement, but it's not the end of the story. Russia still faces significant challenges in scaling up production, ensuring long-term reliability, and closing the gap with Western competitors. Manufacturing 4 turbines per year as Rostec has planned is a solid start, but it's far from mass production. Expanding output requires more factories, more trained workers, and more investment in advanced manufacturing equipment. Quality control is another ongoing concern. Western manufacturers have refined their production processes over decades, achieving extremely tight tolerances and consistent performance across thousands of units. Russia is still building that track record. Every turbine that enters service provides valuable data, but it takes years of field operation to fully understand how these machines perform over their entire life cycle. There's also the issue of innovation. Siemens, GE, and other global leaders continue to push the boundaries of turbine technology, developing more efficient designs, smarter control systems, and cleaner combustion processes. Russia is catching up, but maintaining that momentum requires sustained research and development. Isolation from international supply chains and collaboration networks makes this harder, though not impossible. Political and economic factors play a role too. Sanctions limit access to certain materials, components, and technologies that could accelerate progress. While Russia has proven it can work around these restrictions, doing so adds time and cost to every project. The long-term question is whether domestic innovation can keep pace with global advancements, or if the gap will widen over time. Despite these challenges, the trajectory is promising. The GTD 110M has already proven itself in real-world conditions. With continued investment and focus, Russia has the potential to not only meet its own energy needs, but also position itself as an exporter of turbine technology. Countries facing similar pressures from sanctions or seeking alternatives to Western suppliers could become future markets. The GTD 110M is more than just an engine. It's a symbol of resilience, a testament to what can be achieved when necessity drives innovation. The road ahead is long, but the foundation has been laid, and Russia is moving forward one turbine at a time.